We studied the effect of the increasing wall-to-wall distance on the nematic ordering of the quasi-two-dimensional confined systems of hard cylinders and ellipsoids. In the figures, all the snapshots correspond to the same two-dimensional particle number density, 0.28, and aspect ratio, kappa equal 5. The panels on the left correspond to the strictly two-dimensional case, where pore width, h, equal with the shorter length of the particles, sigma. In such a strict confinement, there is no room for transverse fluctuations. In the right panels, the wall-to-wall distance is doubled. This is the widest pore which still maintains the quasi-two-dimensional character of the system, that is, the particles located at opposite walls can interact directly with each other. Regarding the wall-particle interactions, in the most simple case we assume that the particles adsorbed at the walls. The figures here belong to this case. As it can be seen, the system of ellipsoids turns disordered as the pore becomes wider, as expected naively too, because more room means less three-dimensional density, thus the hard-body interactions become less important and the system turns less ordered. On the left panel the phase is nematic, while on the right panel the three-dimensional density is only half of the value of the left panel and the phase is isotropic. Surprisingly, the cylinders show the opposite behavior. In the narrow pore the phase is isotropic, while in the wider pore the phase is highly ordered nematic. The order parameter is about 0.7. This amazing behavior is the point of our paper. We have also found that when the particles can move freely between the walls, the above effect is still present, however it becomes weaker. Moreover, we have studied the behavior of the plate-like particles too, where the nematic ordering is more complex and both stabilization and destabilization effects can be induced by the walls. A simple geometric consideration can support our result. In the case of the two-dimensional limit, the top view of the confined system shows that the particles look like hard rectangles with the same aspect ratio as the cylinders. However, the wider system is different. On the one hand, the projected rectangles can overlap, therefore there is more room for the particles, which favors disorder. On the other hand, the mutual effective shape of the particles located at opposite walls is a needle, which has an infinite aspect ratio. This favors the nematic order. Effectively, this two-dimensional mixture of the blue and green particles can be approximated by a monodisperse system of particles with an effective aspect ratio and an effective particle cross-section. This effective system has less packing fraction, but a larger effective aspect ratio, and it turns out that the later one is more important. This geometric argument can give us a simple picture. However, it cannot explain the details of the more elaborated behavior of the plate-like particles. Moreover, it cannot provide quantitative results. Therefore, we employed the second virial density functional theory to study the different systems. We derived the isotropic nematic phase boundaries and the nematic order parameter as the function of the pore width for different aspect ratios, both in the strongly and in the weakly adsorbing cases. Moreover, in the later case, the local density and the local nematic order parameter profiles were also computed.